Continuing our Sunday morning at the Church of Foundation, we have Lucien, who's reformulating quantum theory.
So I wanted to give a title that was conveyed somehow the emotions behind this work. You know, people usually give technical titles. I wanted to give a title that conveyed just how emotional this whole thing has been. So here it is. This is the title. I think you'll agree. This is really very emotional. So the question I want to ask is why?
Why not?
We're going to be here a while.
Okay. So in particular, why quantum theory?
Why not quantum theory?
Good question. 10 years ago, I posted a paper on the archive.
Are you saying this paper you posted 159 years ago?
No. This is just 10 years ago. And this paper was, in this paper I derived, the title of the paper was Quantum Theory from 5 Reasonable Axioms. And the idea was to try and give a set of somehow reasonable axioms from which you could derive quantum theory. And for the most part I was happy with that paper, but there was one axiom I really didn't like. It was a kind of simplicity axiom. It forced you to take the simplest case that was compatible with the other axioms. And for me that wasn't really very satisfactory. So for 10 years I've struggled with this. 10 years of near madness and crazy, incredibly difficult 10 years. A lot has happened in 10 years. I got married, had a kid, but all the time I've been working on this problem. And then 13 months ago I was here in Bellairs, and at the end of my talk someone, and I'm pretty sure it was Bill Edwards, but it might have been Ross, 90% sure it's Bill, asked one of those annoying questions. I wrote down an equation. He said, why is that equation so complicated? And he kind of got me thinking. And out of that came the duotensor framework. And once I got the duotensor framework in place, it was possible to move on to readdressing this question that's been bothering me for 10 years. So finally, this week, as I was flying on the plane to Barbados, I finished writing the paper. This is an earlier draft. I haven't printed it out yet. And the paper is, well, guess how many pages long? It's not a short paper. Okay, so I think you'll agree this conveys very accurately the emotional content of this. So this is based on something I call the circuit framework. The circuit framework is kind of what you think it is. It's just allowing yourself to draw circuits, represent experiments by circuits where you have boxes and wires connecting them. And I won't go into any detail about that because I don't think I'll have time. And I'm going to give some operational frameworks, some operational postulates from which you can reconstruct quantum theory within this circuit framework. So incidentally, I'm very happy to take questions, of course. So before I can give you the postulates, I need to give you a bunch of basic ideas, most of which I imagine are pretty familiar, but still, let's go through this. So, first idea is the idea of a maximal set of distinguishable states. So imagine we have preparations. So I have time going up. We have various different preparations. And from all the different sorts of preparations that we have, for a system of a certain type, this is the type. So this could be for a spin-half particle, for example, or something else. Of course, we're being more general. We're not talking about quantum theory in particular, just general physical theories, we have preparations. It may be that you can find subsets of preparations which can be distinguished by some measurement. So here's a subset of preparations. There's a label n. So we have n equals 1 up to big N. This is for the particular type of system. In order for this set to be distinguishable, I want there to exist some measurement which has outcomes labeled by M, and it has to be such that we get the probability, if I send in a preparation labeled by N, then I certainly get the corresponding outcome up here, and I get 0 probability other ways. Okay. So if that is true, then there exists a measurement up here which distinguishes this set of states. And I want this to be a maximal set, so I want this to have the maximum number of elements. So there shouldn't exist any set of distinguishable states that has more elements than this. Of course, it may not be unique. There may exist many sets for a given type of system. There may exist many sets of distinguishable states with this number. Is that clear? So here, NA is an important property. This is one of the things that characterizes your system type. And so obviously, if you have, say, a spin half particle, then NA is equal to 2. It's just in the case of quantum theory, this is just the dimension of the Hilbert space. Okay. So the next notion I want to talk about is the idea of states. So states are associated with preparations. So here's a preparation for a system of some type. And of course, I can put many different, I can close this into a circuit in many different ways. Okay, so here I have a preparation A. Then up here I have a measurement with a particular result, a particular outcome singled out. Okay, and I call that a result. So this thing is a preparation. This thing is a result. And so I can have many such things in principle. There are many things like many outcomes of many measurements I could put on top of my preparation. We can think about the probability of seeing this particular thing happen. So the probability that this preparation is successful and that we see the outcome associated with this result. This is a very long list of probabilities that we can imagine. Now, generally, in physical theories, these different quantities are related to each other. So, for example, in the case of quantum theory, the probabilities for seeing, when you have a given preparation, and then you look at the probabilities associated with different outcomes of different measurements, then those probabilities are related to each other in some linear way. And indeed, we can just ask in general, rather than taking this full set of all probabilities of all conceivable results, we can compress ourselves down to a smaller set. problem in giving this talk on a blackboard because I use two different fonts in the paper. For the types representing the systems, I use sans serif font. Whereas for this, which is just a label, an integer label, which runs from 1 up to some case of A, I use just ordinary mass font. So I'm going to put an orange circle around this one. Okay. Just to indicate that's a different font. So the idea is that I should be able to compress down to a shorter list of probabilities. And from this shorter list of probabilities, I can calculate any of the probabilities in this longer list by a linear equation. Okay. So I can always try and do that. It may be that I don't succeed in compressing at all, in which case I just have a list which is as long as the one I started with. But in general, you can expect that you will be able to compress. And I'm going to call this thing, I'm going to represent it by just this. Okay. So this list of probabilities, I'm just going to represent it by this object.
So the compressed list doesn't have to be a distribution.
No. In quantum theory, it will not. Generally, it will not be a distribution, although you can leave it in a distribution. Okay.
Lucien, can I ask you something? I want to ask before you get to the end of the talk, that I'm probably going to forget. But you said you had these 5 postulates, right? And you said the one that you were uncomfortable with was the simplicity, right? Yeah. I don't remember what that one is, but I remember there's this other one that says there's a continuous reversible transformation. Are you okay with that one?
You didn't like that?
No. I thought it was.
That one's gone as well, actually.
Oh, is it gone?
Yeah. So the new set axioms are better than the previous set in many respects. So now you can derive the kind of transitivity property, at least, that axiom before, and you get the continuity property in the end. Yeah, so that's also gone.
Oh.
Yeah. So, okay. Sorry, my notation is a bit badly. What I really mean is that A is just equal to the probability associated with some particular result, and then I have the list of these probabilities going from 1 to case of A, and that list of probabilities is sufficient to specify the state. So what that means is that if I have something like the probability of AB, that should just be given by a linear expression. Like so. Incidentally, in the paper I also use sans serif font for that, but it's going to get complicated if I draw a lot of orange circles. Sorry, I also use sans serif font for this, and I use normal mass font for this. But this is more important. This A is a label going for one test. Okay.
So there's some summation here?
Yes, so summation is in. There's really a disconnect between this being an A and this being an A.
But where are we storing these coefficients and using this extra? We perform this compression, but we still have to retain that with all these coefficients so that we can recover our long list of functions.
So what it is so associated with any preparation, you have a state. So this is what I'm trying to define a state. So this object is a state here. And then associated with any result, the thing up on the top is an effect. Okay. So the place that information is being stored to decompress this is in the specification of the effects. Any more questions? I mean, this is fairly standard stuff in lots of different operational approaches to quantum theory, sort of complex probabilities framework. You'll see maybe not this notation, but this basic structure. Okay. Yes, actually, incidentally, we've introduced a second important number here, which is case of A. A here is the type. Like, it's an electron of all of it. Okay. So now, once we define what we mean by states, there's a few important concepts we can talk about. So pure states are states which can't be written as convex sums. So mixed Mixed states are states which can be written as convex sums. So a state is mixed if we can write lambda A prime plus 1 minus lambda A double prime, where lambda is greater than 0, less than 1, and A prime and A double prime are distinct states. I think that would be a mixed state. If the state is not mixed, then it's a pure state. Okay, good. Nice. So the next thing I want to talk about is filters. So remember we had this measurement here, which can distinguish a maximal set of distinguishable states. We call measurements like this maximal measurements. Each outcome of a maximal measurement, in other words, each particular value of m, is a maximal result. And then associated with a maximal result is a maximal effect. So in a sense, preparations are to states as results are to effects, and we have all these different concepts we can talk about here. So the next thing I want to do is talk about a filter. So filters, so F can be a filter, and it's defined with respect to one, a particular maximal measurement, and two, some subset of the outcomes of that maximal measurement. So for example, OF might be equal to 1, 3, 7. Some subset of the possible outcomes of the maximal measurement. And a filter has to have two properties. So in the case that we have preparations which only give rise to non-zero probabilities, when the outcome M belongs to this set, then if you send this preparation onto the filter, the state passes straight through unchanged. In other words, it means that this is equivalent to this. Okay, so that's a fairly standard. Okay. So if the state has support in the outcomes associated with this set, given by this set, then the filter doesn't affect the state. The preparation is the same thing. And if we have a preparation which only has support in the complement set, then the filter blocks the state. In other words, if you have the state followed by the filter, that's just equivalent to having the null state, the state which gives zero probability for every result.
Can you say something quick about what you mean by probabilities in this?
Yeah. So when I define the circuit framework, so a circuit is generally given by something like this, and I've suppressed I've suppressed in this drawing the structure associated with outcomes. You can draw it like this. There's some outcomes on this device. Okay, that's really encoded in the notation A, and likewise here. And then the probability for this circuit is just the probability that I see this outcome and this outcome. Okay. So it's a joint probability. Okay, and you're asking what is the interpretation of probabilities? Yeah, so I tried to sidestep that question. I mean, you can interpret probabilities in lots of different ways, as Bayesian probabilities, as propensities, as frequencies. As long as this probability satisfies the usual sorts of postulates, that they add to one and you have equal, then we're okay. Yeah, and then one thing I do assume in the circuit framework is that you can give a probability for a circuit, and that probability is independent of any other circuit you may have around that are disconnected from this one.
Could they be valued in an abstract space rather than 0, 1?
I don't go there, but maybe one could go there. Yeah. I mean, I assume my probabilities are between 0 and 1. I think that's essential for the reconstruction. But maybe if you drop that, you would get some more general classifiers.
This null set that gives zero probability for everything.
Yeah.
Is that like the zero vector?
Yeah. So if it was written as one of these vectors A, then all the components are equal to 0.
Right.
Yeah, and so that means that when you take, yes, so when you take, that's right. You get 0. Okay. So this definition of filters just corresponds to the normal idea of filters, that they pass things that are in some specified quantum theory to be in some specified subspace with respect to given other space, and they block stuff in the complement of other space. But it's a more general operational definition that we give.
Lucien, what are the states here? Are you just assuming it's some set of things that are called states, and they give rise to these probabilities?
So the states, I went for that construction where I talked about all the different ways you could close the certain different things, and I had this long list of possible probabilities.
Okay.
Then I said, well, you can compress that down to a smaller list. And if you compress it down optimally, so you can still reconstruct the bigger list by a linear expression, like I gave. Then that compressed thing is my state. So now those things, we would want them to belong to some set of possible states. And part of the problem of reconstruction is to show what's the characteristics of that bigger set of states that they belong to. Also, when you reconstruct, you have to characterize what's the nature of the set of results. The results are associated with effects, and the effects are really just the coefficients in the expansion. So yeah.
So then what a state is it sort of it's this compressed list of probabilities that you can use to reconstruct?
Exactly, yeah. So you're choosing a particular fiducial set of results. So basically, a fiducial set of outcomes associated with measurements, just a special set that you choose for that purpose. But given that special set, you can reconstruct probability for any result.
So should there be a unique way of doing it?
No, generally there's not a unique criteria. Yeah, and there's no reason for there to be. So basically, you're kind of choosing a basis.
So then when you compose things, like the indices up and down,
Yeah.
so these you have to make sure that you get these match up.
Well, it has to be the same with respect to the same basis. Yeah, that's right. Yeah. These objects kind of transform. So if you change your basis, then they transform like tensors. Basically. There's a more general class of objects like this that transform as well. I call pure tensors. They're a more richer class of things. But for the moment, these things are just like tensors. They transform into the sort of in the way you'd expect. If you change your fiducial set of results, then you vector transformation.
Do you think of these states as states of something? Is there
So I try to be as operational as possible. So I told you how to construct these states. Now you're asking me a philosophical question. Right. So whatever my answer would be to that, it wouldn't affect how the reconstruction works. I don't know how I think. It really depends what you think of as probabilities. You know, so if you take the sort of Lucien approach, you believe probabilities are states of belief, but then they wouldn't be states of your underlying system because they're states inside your brain. It's a big debate. You know, it's a big kind of worms. So. Okay. Move on to right. The next concept. Actually, one thing I meant to talk about here was so we have pure states and mixed states, and you can imagine some transformation. So I call the transformation non-mixing if whenever you send a pure state in, you get a pure state out. Okay. Actually, there's a slight subtlety. I don't mind if this pure state is only pure up to normalization. So it could be proportional to a pure state. It could be a mixture of a pure state and a null state. So a non-mixing transformation is one which, when I send a pure state in, I get a pure state out up to normalization. Right. How do I do it for time? Okay, so I want to give this definition, this idea of a non-flat set of states. I'll just write down the definition. So a set of states is said to be non-flat if it is a spanning subset of the full set of states that are passed unchanged by some filter. So imagine you have a set of states and you want to know if they're flat or not, according to this definition. Well, you look around, if you can find a filter which is such that this set of states in your candidate set spans the full set of states that are passed unchanged by this filter, then you have a non-flat set of states. So in the case of quantum theory, a set of states will be non-flat if they all had support on some given subspace of your Hilbert space for the system, and they spanned that Hilbert space. I'm talking here about projectors, about density matrices. So they have to span the space of the Hermitian operators to act on that given subspace. But this is a more general operational definition.
So in general, you mean spanning in the sense of you can reconstruct the bigness, the probabilities by this linear equation that you had before.
What I mean is, I have some filter. Here's the set of all states, things like this, which pass through the filter unchanged. Now I have a subset of states which are in my candidate set. It's called D, some index, and so I've got I going over my subset. I should be able to write any state in this full set of states as a linear combination of the states in this set of states. Yeah, so this state span this subspace. Is that clear?
So what would make the set flat?
We're not non-flat.
Yeah.
I don't know. I just what I came up with. I mean, it seems if the set is flat, then it's got fewer dimensions. It doesn't sort of live in the full space associated with this filtering. It's not sort of fully. It's not fully it's not fully spanning this space. Yeah, it's like a low-dimensional plane. Yeah.
So you call it full? This thing is full?
I could have done.
I'm just saying.
Yeah. My wife bought me for Christmas this toy, which is a sort of like a star that expands out, but then you can squash it flat into a low. It's actually three-dimensional, of course, but you can squash it into one dimensions. And it just seemed that squashing it flat was the way to think of it. Squashing it down. Yeah.
Can you explain intuitively why it's not always possible for any set of states to find some filter generally passes spanning those?
So let's give a piece of quantum theory. So taking quantum theory, if I have a filter, so I imagine I have a set of two states. Okay, they can just be, I've got a bigger Hilbert space, say a five-dimensional Hilbert space. And my set of states just consists of the zero, so the one state and the two state. It's an orthonormal set. Okay, so that's a set of states I can test. Now that set of states will pass through the filter that projects onto the 1-2 subspace. And you're not going to find a smaller, you're not going to find any smaller subspace than that. They'll pass through. And clearly those two states do not span the space of the Hermitian operators associated with that, because that space is not.
Do you span the full space which is passed by that?
No. They span on the Hilbert space, but not of the projection operators that not of the space of the Hermitian operators. Because states in quantum theory are given by density matrices. So density matrices live in the space of operators that act on. Is that clear? Okay. So you can prove actually that in quantum theory any non-mixing transformation is also a non-flattening transformation. I should define what I mean by non-flattening transformation. So a transformation is non-flattening if whenever you send a set of states in that's non-flat, the set of states that come out is also non-flat. That's not a trivial statement, because it could be that the set of states that go in are actually, for example, in quantum theory they could correspond to a five-dimensional Hilbert space. But the set of states that come out could correspond just to a two-dimensional Hilbert space. But nevertheless, if the original set of states are non-flat and then the final set of states are non-flat, and that's true for any input non-flat set of states, then I'd say that the transformation is non-flattening. Okay. And so it turns out in quantum theory that non-mixing transformations are also non-flattening transformations. It's not completely trivial to prove that, but not too difficult.
Lucien, these transformations in the case of quantum theory, are they just unitaries?
No, the more general class of CP maps. So
Is that exactly what it works out to be? The class of CP maps?
yeah, it works out to be the class of completely positive trace non-increasing maps.
Okay.
They can decrease the trace. In fact, filters decrease the trace, for example. Yeah. So of course I'm trying to give general operational definitions because I don't want to assume quantum theory. Okay. Right. So I think now I have in place all the concepts that are necessary to give you the postulates.
Flattening transformation or something that throws away part of the state?
Well, let's see. So maybe this is an example of a flattening transformation.
So what about a filter by itself?
No, actually, sorry, I meant to say filters are non-flattening. And that's one of the postulates. Filters are both non-mixing and non-flattening. In fact, you can see that filters are non-mixing because if you send a pure state in quantum theory, you just cut off the state.
So I thought they were flattening, that's why I was
Yeah, yeah. So filters. So one of the postulates, the last one is going to be that filters are non-mixing and non-flattening. Actually, generally, I haven't quite been able to. There's a conjecture in the paper. I haven't been able to prove that in this general operational framework that the other postulate that any non-mixing transformation is non-flattening. But generally, it's difficult to imagine how non-mixing transformations could be flattening because they've got to make sure that the states are still proportional to pure states afterwards, and the pure states are extremal. If you squash yourself flat, they end up in the interior. And so there's a relationship between those concepts, which I haven't been able to prove. I decided to. No, I mean, I used all things to try to prove that. Yeah. Okay. So the postulates. I'm not entirely happy with the names I give for all the postulates, but I think of better names. So the first one is definiteness. So here's the idea. Seems like the gods are not too happy with this. I'll read it out first, then I'll write it down in abbreviated form. So definiteness. So the idea here is that associated with any given pure state is a unique maximal effect given probability equal to 1, and also that this maximal effect doesn't give probability 1 for any other pure state. Okay, I'll write that down. So basically this is saying that there's sort of one-to-one map between maximal effects and, between pure states and maximal effects, which is kind of what you'd expect. I mean, maximal effects are somehow the most, the sort of most fine-grained measurement that you can make. And pure states are the states which have a sort of maximum knowledge. You can't have a state which is purer than a pure state. And so you'd expect that they're associated with maximal effects, and this postulate just makes that association clear.
sort of operational definition of pure state?
Sorry?
What's the operational definition of pure
So I
state?
gave it earlier. It's an operational state is associated with preparation that can't be simulated by a mixture of preparations. Of course, I gave you the definition. It can't be written as a complex combination. It's the same thing. Okay. So the next one is information locality. So incidentally, this did exist in my original paper from 10 years ago. And I'll read it out. So this says that a maximal measurement on a composite system is affected if we perform maximal measurements on each of the components. So imagine you have some composite system having many components, and then you perform maximal measurements on each of those components. And then you look at what kind of measurement you've affected in total, but that should also be a maximal measurement, according to this. Maximal measurement on the composite is affected by maximal measurements on the components. A different way of, an equivalent formulation of this is that this is true. So if I have a composite system of type AB, then the number of states in a maximal set of distinguishable states should just be given by the product of the number in each of the two subsets. That's equivalent. It's equivalent to my this postulate.
So this goes both ways. You've done a maximal measurement on the composite.
Yeah.
There are maximal measurements you can find on the components.
No, it doesn't go that way. That's not true. And that's not true in quantum theory either. This just says if you make maximal measurements on the components, then you affect a maximal measurement on the composite. Yeah. Yeah. But in quantum theory, that wouldn't be true because you can perform measurements in an entangled basis.
Yes.
Yeah.
Should those A's and B's have circles around them?
No, because the ones with circles are just labeled as integers, whereas these are type. Okay. Postulate P3. Tomographic locality. Just check. It means I don't have to tell you how I actually get quantum theory from this postulate. So all the time to go through that part of the bit. Postulate 3, tomographic locality. So this says that the state of a composite system can be determined from the statistics collected by making measurements on the components. I'll write this down. So imagine you have a composite system, you know, A and B, and I'm trying to determine. I've got some states for that, so I've got some preparation. It prepares a state, and I'm going to make measurements on many instances of that preparation, and I want to determine what the state is of that composite system. Well, the postulate says that it's possible to do that by making just measurements on the components and looking at the joint probabilities that you get. Okay. And this is true in quantum theory. This postulate is very natural, and you'll find it in many of the reconstruction attempts have in recent years have this postulate as a basic one. It explains why you have complex numbers rather than real numbers, for example, in quantum theory, and it's equivalent this. Remember, K was the number of probabilities in your vector representing the state. So P3 is equivalent to saying that this thing factorizes in this way. It's very similar to this.
Do you allow for some sort of limiting procedure in P3? I mean, in general, if you do tomography, you need many measurements, right? And only in the end, in the limit, you know something about the state.
Oh, right, yeah. So, you mean you have to build up the statistics. So I'm just assuming we have, an infinite ensemble, or what depends partly what our interpretation of probability is. If we have a different interpretation, we may have to have a different procedure. But yeah, I'm assuming that we can get our probabilities somewhere, maybe by measuring.
Well, it's not purely philosophical. I think this goes directly to sort of operational. They're aiming for an operational interpretation.
That's what I'm saying is I'm helping myself to probabilities for circuits as a free without discussing how you get those probabilities. So I'm saying that any circuit, this is the kind of circuit we'd be interested in this case. Okay. So have some state, some preparation of as a state. I'm helping myself to these probabilities. And then what this assumption is saying is that this probabilities can be used to with different you have to use different results here. Can be used to reconstruct the state associated with this preparation. Now, sure, if you actually want to do that in the laboratory, then you've got to collect enough statistics for that purpose. I'm not worried about that side of things. I mean, there is a whole question that's raised here, which is, if you were to think more carefully about probability and have a deeper appreciation of it, maybe that would lead to a deeper reconstruction of quantum theory. My attitude is, the interpretational problems with probability are already quite difficult. So I'm kind of putting those to one side and just taking probabilities as given. Okay. P3. P4. I guess I need to. P4 prime. What I didn't tell you was that this set of postulates I'm writing down now give you both classical probability theory and quantum theory, and no other theories are consistent with them. If I want to get quantum theory, I have to modify P4 prime slightly. And I'll talk about that in a moment. So P4 prime is commutatability. So the idea is, I'll read it out, is there exists a reversible transformation on any system affecting any given permutation of any given maximal set of distinguishable states for that system. Okay. Okay, sure. There exists a reversible transformation on any system affecting any given permutation of any given maximal set of distinguishable states for that system. So imagine I have some system has 3 distinguishable states. So I have some set of 3 distinguishable states, 1, 2, and 3. I can find a reversible transformation that commutes them, so 1 can go to 3, 2 can say where it is, and whatever the other. Yeah, commutes them in any way. So this is a very classical notion that I can. It's just given some set of distinguishable states, which is kind of classical. It's a classical idea anyway. I can commute them by some transformation in any way I want, in a reversible fashion.
Quantum theory is saying something like the permutation group acts unitarily on the state space.
Yeah, it's true. Since I don't want to talk about unitary
I understand.
So these would certainly be unitary transformations.
Interesting because in two-dimensional quantum theory, perhaps you would want a different group for us. The weight group that you react on in permutation.
So postulate P4 prime, there exists a reversible permutation with respect to any maximal set of distinguishable states. Postulate P5. So I told you this already. I call it preparability. So this is the assumption that filters are non-mixing and non-flattening.
Sorry, what's that word say before states?
This one,
Yeah.
distinct. So
Distinguishable.
distinguishable, yeah. So distinguishable, yeah. So there exists a reversible permutation with respect to any maximum set of distinguishable states. So the last one, the last postulate P5, I call it preparability. And this is the postulate that filters are non-mixing and non-flattening. And then what I prove in the paper is that for finite dimensional quantum theory, for the finite n case, this set of postulates is consistent with only two theories, which are classical probability theory, which is where you have states as just distributions, can be given by just distributions, and maps as stochastic maps and so on. And then it's also consistent with quantum theory, and nothing else. Okay. So just those two theories are consistent with this set of 5 postulates. So in particular, in the previous paper 10 years ago, I had this relationship that k is equal to n to the power r. This really follows really from these two assumptions, or you can see it from here. If you have these two things, plus a few more natural requirements that follow from the postulates as well, then you can prove that k is equal to n to the power r. And I show that there's only two values that are consistent with these postulates, only two values of r that are consistent, which is r equals 1, the classical case, and r equals 2. And then, of course, in addition, you have to get all the structure of quantum theory, the sort of CP maps and states being represented by density matrices and so on. Get all that from these postulates after 150 cases. If you want to set 5 postulates that give rise to just quantum theory, so you rule out classical theory, then you can add anything you like, which is consistent with quantum theory and yet inconsistent with classical probability theory. Okay, so anything will do, which is kind of sad because I started this talk with the question why quantum theory. Well, it's sort of the answer from this kind of point of view is any reason you want, as long as it's inconsistent with classical probability theory and consistent with quantum
That
theory.
kind of presupposes you know the answer.
Sure, yeah.
I mean, could I ask, what is, probably an annoying question, but I mean, what is this, how should we think of the status of these postulates?
In what sense?
Well, I mean, why should we, so we would like to understand why quantum, I suppose that's the question, why quantum effect?
Yeah.
So, these don't look like sort of like the laws of thought or whatever. So they, so why are they compelling?
Right, that's a good question. I spent some time in the paper talking about why I think each of them is compelling. Some of them I think are more compelling than others. The tomographic locality I think is very compelling when you start to look at those models. If you don't have that, there's a lot of things difficult. It's sort of, it's not quite, but it's almost saying that you can do physics in a kind of local way by taking one part of the world and so this enables you to specify some part of the world and then specify another part of the world, and then the joint specification of those two things is just given by the specification of those two things separately, and that works in this sense. So I think each of these is compelling, but maybe not as compelling as one wants. I don't think this is the final word.
And would you distinguish between, you just said that was particularly compelling one?
Yeah, everyone uses that. And I think also this one is pretty compelling as well, the information locality. I mean, even this, I think, is pretty compelling, that you should be able to, if you've got some set of things that can be distinguished, that you should be able to mute them. Otherwise, it's very difficult to sort of do stuff in the law, you know. I mean, perhaps the reversibility requirement is a bit stronger than the weapons, but commutatability, I think, is a very natural thing to be able to do. This one, I think, well, number 5 and number 1, I think, are the less natural postulates. And it's interesting, the way the proof works is just from postulates 1 through 4 prime, you get a lot of structure. And you only need this postulate sort of after you've already built a lot of the structure that's necessary. So maybe you can find an alternative for this.
So what does that in particular give you, this P5?
So there's some key things in the